Platonic solids today. So here we go. This is a wonderful moment in your life, and I guess we'll just like repeat this moment later. Can you like everyone come here? Jenny, can you help?
We get to hold the polyhedra.
You can hold them. Be very careful. Make sure your hands are not dirty. Okay. Okay, is someone going to go handheld with the camera or just like point it down? All right. We're now talking about polyhedra. This is the climax of your entire secondary education. Yeah. All right. Here are the Platonic solids. Make sure you zoom in. They are beautiful. They were made by Project Polyhedra, founding member in the room right now. It's a tetrahedron. What is a tetrahedron? It is a regular polyhedron. What does it mean to be a regular polyhedron? It means that you have faces, and the faces are all regular polygons. A regular polygon is the polygon whose sides are all equal and whose angles are all equal. So, for example, if you have a three-sided polygon, that's called a triangle. Then we're talking about equilateral triangles. So this is made up of equilateral triangles, and it is irregular in another respect. So one of the reasons why it's regular is because all the faces are regular polygons. But the other reason that it's regular, there's some fancier ways to say this, but generally speaking, every vertex is regular in the sense that the same thing is going on at every vertex. What's going on in every vertex of a tetrahedron is three triangles are meeting at every vertex. Okay, and so what we have is this gorgeous shape, all of whose faces are equilateral triangles. It's more than just the same thing going on in each vertex. It's composed of all one kind of polygon, and the same number of them meeting at each vertex. So tetrahedron, composed of equilateral triangles, three meeting at a vertex. It has all kinds of amazing properties. There are four faces. There are how many edges? Six. How many vertices? Four. Woo! The next one, the cube. It's composed of regular fourgons called squares, three meeting at every vertex. And it is composed of 8 vertices, 6 faces, 12 edges. 4. Yeah? Woo! The octahedron. Oh, I love the octahedron. One of my favorite 5 Platonic solids. It's not even funny. It is composed of equilateral triangles, 4 meeting at a vertex. Note how you can describe its the overall global shape by virtue of like its local properties. So what can we say about it? It's got 6 vertices. How many edges?
8.
Edges?
12.
So 4 around the midline, and then 4 more. 12. And 8 faces. That's why it's called the octahedron. Then you have the dodecahedron, composed of regular pentagons. And there are 12 regular pentagons, hence dodecahedron is the Greek prefix for 12. And then there's just like a crap load of edges. I happen to just know by heart that there are 30 of them. Actually, you can count them pretty quickly. There's like 5 on the top, 5 on the bottom, 5 coming down from the top pentagon, 5 coming up from the top pentagon. So that's 5, 10, another 5, so that's 20. And then there's 10 on this like zigzag through around the sides. So that's 30 altogether. How many vertices? Well, again, 5 on the top, 5 on the bottom, and 10 on the zigzag, so 20 vertices. Okay, and finally, the icosahedron, 20 faces, all equilateral triangles, 5 meeting at a vertex, 30 edges, what did I say? 20 faces, and 12 vertices. Okay, these had like a mystical significance for the ancient Greeks. They obsessed over them. There were all kinds of theories that they were like the building blocks of all like three-dimensional objects. Are you taking what's it called class now?
Took origins of science.
You took origins last year, yeah. Like the tetrahedron was associated with like fire because it was like the sharpest This one was like Earth, I believe, because it's like the most stable. It like tessellates space by itself. I might be having this backwards. I don't remember which is which. One of them was like air, earth, air, fire, water. I actually literally don't remember which is which. And then like they ran out. Those are like the 4 traditional elements, but then there's 5 of these. And then they were like, and the ether or something. I don't remember what the hell they said. But Euclid in the Elements concludes with a book about polyhedra. And so you might think of the entire reason for writing the sort of founding document of Western mathematics is just so that you could prove that like a dodecahedron exists, which is like literally the last thing he does. It's the second to last theorem of the last book of Euclid. Yes?
You got it right. It's Earth is the cube, air is the octahedron, water is the icosahedron, and fire is the tetrahedron.
Yeah, so this is like water because it like rolls nicely and flows and stuff because it's like very spherical. This one is, what is this? Air?
Yeah.
Air, just for like, I don't know
They
why.
ran out.
This one's like sharp, so it's like fire or some crap like that. This one's like earth because it's like stable. And then this one's like the ether.
Yeah, I guess.
Yeah, some crap like that. Okay, good. We are going to do as much polyhedron learning as we possibly can for all the classes that we have left. What's
Air
up?
is made of octahedrons.
Why are there only 5 is a brilliant question, which we are going to begin to answer today, and we are going to finish answering next class. Why are there only 5? All right, middle schooly type proofs are available for why there are only 5, but what we are going to do is to do like a sort of kind of more general topological proof, which does not prove that there are only 5 for like geometry reasons, but to prove that there are only 5 for like graph theory reasons or something like that. And really, the sort of history of these is that they were thought of as like actual geometric objects, as you probably think of them now. And they were drawn traditionally like this and thought of like this, as like solids. It was not until Leonardo da Vinci, who was interested in the like properties. This is sort of like a proto-graph theory thing that he did. Have you seen these famous pictures that he drew of like polyhedra, in which he drew them hollow with the faces transparent, so that you could sort of see what was going on behind, so to speak. He was the first person to ever do that. And what he revealed about the polyhedra is that perhaps they were best thought of as just a collection of points and edges. And it was not until the time of like the 16th to 17th century, even though people were obsessing over these, that people began to think of them in a discrete sense instead of like as in a continuous geometry sense. And what we can do is, in fact, think of these discretely as really just, and then we sort of don't care so much anymore about like the particular position that the vertices and edges take. You would just describe a cube as a graph with 8 vertices, 12 edges, and it's a regular graph, so every vertex has degree 3. And in fact, cool, people obsessed over these polyhedra, and in fact proved an important theorem, which there's an entire history of why no one freaking thought of this before. This is called, well, okay, there's a lot of things called Euler's formula, so I'll just call it Euler's characteristic formula. But I might but I might get lazy and just call it Euler's formula. And originally, this was okay. Well, here we go. What does it say? It says, let me make sure I get this right, that if you take the number of vertices plus the number of faces minus the number of edges, 8 and sure, that's just like true, yeah, then you get 2. This is like amazing, incredible, blew people away, and was just shocking and wonderful. And Euler was the first person to notice this and was the first person to prove it. When he proved it as like a theorem about polyhedra. And he proved it sort of like on the polyhedra, so to speak. I think this is true. But it can be sort of rephrased as a theorem about graph theory, because every one of these polyhedra can be sort of redrawn in a graph, especially if you're willing to accept the fact that like the infinite region outside your figure is just another region. And so we may draw a so-called planar embedding of the cube. And the planar embedding of the cube looks like this. Notice that it, just finish. Notice that it obscures the cube's geometric properties because we're deciding temporarily that we don't care about them. But it preserves the cube's combinatorial properties because the cube, after all, has 8 vertices. Here they are. Every vertex has degree 3. Check. Every vertex is the meeting of sort of 3 faces. The faces are all just 4 cycles. And there are 6 faces, and the 6 faces are 1, 2, 3, 4, 5, and everything else. And you can sort of see that cube being made by like looking at the cube, sort of remove a face, so to speak, and then just like flatten it out. And this removed face becomes like the outside region. Okay, so we will practice this next class when we're all together, because it's like a fun thing to do for like 10 minutes. And we have a guest speaker, Reynold, who's going to come in and like he got obsessed with this last year. But any, just like fact, more to say on this later, any polyhedra, asterisk on that because it's not quite true, can be turned into a planar graph. And so in fact, the more general theorem that we are now going to prove is not just that this is true for polyhedra, but that this is in fact true for any planar graph, any connected planar simple graph. I think that is true. Yes?
Okay, so, but like, what we're saying here essentially is that like mathematically a cube and like a rectangular prism are basically like the same thing.
They're
We're
not,
just, like, eliminating
they're not the
the
same thing geometrically, but they're the same thing combinatorially or something like
so
that.
like the properties will hold true. No
The
matter
properties
how
that we
kind of,
care
like,
about will hold true.
warp the length. Okay.
Right. That the
Interesting.
actual geometry is irrelevant. All that's relevant is like the connections that vertices have to other vertices. How many? Where are they? Etc. Yep. So indeed, we are now going to prove this, and we're going to prove it for, like I just said, any connected planar simple graph. So given a connected planar simple graph with epsilon edges and n vertices. We need to introduce one more notation. Let rho be the number of regions. The number of regions in a planar embedding. Including the region on the outside. So what's happening here is we're generalizing this polyhedra problem in a kind of a way. Yeah, that's what those are up there. And so we're basically saying like, okay, so first let the graph be connected because duh. Let it be planar. In fact, every polyhedra graph is planar. If you remove a face, it just feels right that you can just flatten it out. That's just like true. But this applies to other graphs that are not polyhedra graphs. So the proof we're about to do is like sort of more general than Euler's one, because his is about polyhedra. Now we're saying the theorem we're about to prove holds not just for all polyhedra graphs, but in fact any graph which is connected planar and simple. And then the corresponding thing we want to prove is the number of vertices, which is n, plus the number of faces. Well, faces have now, in this planar embedding, been converted into regions. Nod if you're with me. Minus the number of edges is 2. This is the goal. Okay, who's with me? Say I'm with you. Good. Here's what we're going to do. What do I have, like 4 minutes or some crap? Perfect. Good. All right, here's what we're going to do. We are going to label all the edges of our generic... Oh, we're going to do this by... well, first let's label all the edges. Okay. And what I would like you to do is to label the edges. Label the edges. Edge 1, edge 2, edge 3, in such a way that the graph remains connected at every stage. The subgraph with only this many edges on it. So in other words, the graph with just edge 1, the subgraph with just edge 1 is connected. The subgraph with just edge 2 is connected. The subgraph with just, etc., etc., etc. In other words,
Edge 1 and edge 2.
sure. Yeah, etc., etc., etc. In other words, sort of label the edges in such a way that as the edges are added one by one to the graph is connected. And one may do this, like just like lemma to be blown off. That like if the graph is connected, you can build it up. You can build up your final connected graph piece by piece, such that at every substage the graph is connected. Cool? Say cool. Okay, good. And now let us define epsilon k to be the number of edges at stage k. And similarly, define n sub k to be the number of vertices at step k. And let rho sub k be the number of regions at stage k. And what we're going to show is that at every stage, as you add an edge, this relationship is preserved. Okay, so there are there are only two places to start. What does G1 look like? G1 is the graph with just one edge. Well, it looks like this. Agreed? Say agreed. Okay, good. So it has two vertices and one edge. So what is E1? Say 1. Number of edges at stage 1. What is N1? The number of vertices at stage 1. 2. What is rho 1? The number of regions at stage 1. 1, because the region is just the void that's out there, right? So that's 1. Okay, so is it true that 2 plus 1 minus 1 is 2? So like check, the relationship holds at this initial stage. Okay, now go to G2, which is necessarily, there's like only one possible way for a graph to be it with you making it up piece by piece. Okay, what's epsilon 2, the number of edges at stage 2? What's n2, the number of vertices at stage 2? 3. What's rho 2, the number of regions? 1. And so does the relationship hold? Yes. Okay, and now we're going to do this by induction. So suppose we have a graph GK. Or he wants to start with GK minus 1 or whatever. So basically, okay, so there are two cases. We're just going to do them both before the bell rings. There's a case in which we add another vertex, and there's the case in which we don't add another vertex, but merely connect two vertices that already exist. Okay. So, case 1, remember, what's happening at every stage is at every stage we are adding an edge. Agree? Say agree. Okay, if at every stage we're adding an edge, then there are only two ways to add an edge, right? One way to add an edge is to make a new vertex and to connect that vertex to a previous vertex. Right? At every stage we add one edge, building up to G. Okay, well if you add a vertex, then what can we say about epsilon, I guess I'm doing this, I guess I want to do K, right? Yeah. What can I say about epsilon K, the number of edges in this graph?
It's epsilon k minus 1
Well,
plus 1.
it's epsilon k minus 1 plus 1, because we're just adding an edge. What can we say about n sub k, the number of vertices?
N sub k minus 1 plus 1.
It's n sub k minus 1 plus 1. What can we say about the number of regions?
It's just rho sub k.
It's just rho sub k minus 1, because we don't add a region by just like adding a vertex floating out in the middle of nowhere. Okay, and then case 2 is that the edge is added between two vertices that already exist. If the edge is added between two vertices that already exist, well now how many edges are there?
N sub k minus 1 plus 1.
Again, I add a new edge. How many vertices are there?
N sub k
It's just the previous one because they don't add any new vertices. And it's, well, how many regions are there? Note that by connecting two vertices that are not already connected, this graph is simple. I partition this region up into two regions, yeah? And so this is necessarily one more region than previously. Well, in both of these cases, the relationship is preserved, right? Here I increased epsilon and n by 1. And here, so that they cancel each other out. And here I increased epsilon and rho by 1. So they cancel each other out. And so the base case is that it works here, and I've showed that in every possible addition of an edge, their relationship is preserved. Thus, for any graph that is simple, planar, and connected, at every stage when I add an edge, the relationship is preserved, and so then the final graph also has that relationship. Follow? Woo!
You just gotta add a region or you add a vertex
Every time you add an edge, you either add a vertex and an edge, or you add a region and an edge. And so if it starts being true, then it stays being true. Beautiful. Woo! We did it. Goodbye.